Good morning and good evening, everyone. I'm Jingjun Zhang, a researcher from Riken AIP, Japan. Today, I'm going to host the TrustML Young Scientist Seminar. Before that, allow me to briefly introduce our Riken Center to our valuable guest, Dimitri. The full name of Riken AIP is the Riken Center for Advanced Intelligence Project. AIP was founded in 2016 as the research center for the MAX AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Masashi Sugiyama. AIP aims to enhance the AI fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in related fields. We would be very grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. Let us sincerely welcome our very valuable guest today, Dimitris Tsipras. He is a postdoc at Stanford University, advised by Percy Liang and Greg Valiant. He obtained his PhD from MIT, where he was advised by Alexander Madry. His research is focused on understanding and improving the reliability of modern machine learning methods. He's going to deliver his wonderful talks titled Controlling Models' Behavior Beyond the Training Data. Hi, Dimitris. Yeah, great. Please get started.
Hello, everyone. Yeah, thank you for the wonderful introduction. It's nice to talk to all of you. So today I wanted to talk to you about how we can think about designing the behavior of our machine learning models, and perhaps it's a slightly different way of doing it, moving beyond the data and focusing a bit on more intuitive and high-level interfaces based on prediction rules. So, so to get started, how do we think about the machine learning pipeline in general? Of course, we don't do machine learning because it's fun, but there is actually some real-world tasks that we want to solve. Let's say recognizing objects in the wild. And in order to train our models to do that, we collect a data set that contains various objects. We annotate these data sets, and then we train a model. And of course, when we have this data set, we can spend a lot of time actually evaluating and improving our models in order to get them to perform well on these data sets. And this is perhaps where most of machine learning research is typically focused. We have a nice clean benchmark that we want to develop methods for. But of course, in the end, we don't care about these models in isolation, but we want to go back and deploy them in the real world. So the real question that we care about is, do our models actually work in the real world? And there is a lot of work trying to understand various aspects of this question, but I want to focus a bit on a more fundamental aspect of, in reality, our models in the end will be some reflection of what we train them on. So the first question to ask is, okay, do our datasets even reflect the real world? And okay, so let's just start by getting a bit more concrete about datasets. And how would we envision this process of collecting a dataset looking like? Well, if you ask someone who's just learning about machine learning, they might tell you that the ideal process is something like you collect a bunch of images from the real world, depicting objects in various different scenes. And then we have highly trained expert annotators that go through this data set and carefully categorize these images into various categories. But of course, this is something that's really tricky to do for the really large data sets. Is there something in the chat? I don't think I'll be able to monitor the chat. So if there's any question that I should be answering, please interrupt me. Cool. So this is not something that such a process, while nice, is not something that could really scale for the really large data sets that we care about in most of machine learning. So what ends up happening in reality is we have a much more scalable process. We start from some set of classes that we care about. Let's say we pick them from the coordinate hierarchy, and then we perform targeted search looking for images of these classes. And then we do some simple and scalable annotation based on crowdsourcing to collect our overall data set. And this is something that scales pretty well. The first two steps are something that you can do automatically with any image search engine. And we have crowdsourcing platforms like Amazon Mechanical Turk that we can use to label examples for reasonable prices. But the question is, how reliable is this process? So if we take a closer look into perhaps one of the very popular image datasets, ImageNet, and you ask, okay, how well does ImageNet reflect the real world that we live in? Well, you see an image of a monastery, an image of a Staffordshire Bull Terrier, and an image of a stage. And all these look pretty good at first sight. These are relatively diverse images that do depict what they are saying. So things look pretty good. But what if I told you that actually these are not the ImageNet labels? I just made this up. These are ImageNet classes, but they're not the actual labels of these images. The labels are church, American Staffordshire Terrier, and acoustic guitar. And this might seem confusing at first. We have these images where you can totally describe the content, at least to some extent, by the labels I originally told you, but the ImageNet label is not the same. So why is this the case? And it makes a lot more sense if you take a step back and ask, okay, how did these images end up here through the collection process that we talked about? So if you focus on this specific image, well, the way we got this image is because we picked the class acoustic guitar and we performed the targeted image search for images of acoustic guitar. And we got this image among many other images of acoustic guitars in many different scenarios. And then we presented this image to annotators asking, does this image contain an acoustic guitar? And of course, annotators said, yes, there is an acoustic guitar in there. So this image label pair, this image and acoustic guitar, made it into the dataset of ImageNet. So from that perspective, the fact that this label exists with a label, this image exists with a label acoustic guitar is nothing really to surprise us. But of course, if we think that we never asked annotators about any other possible labels, this clearly deviates from the way that we view this image as a reflection of the real world, right? Like clearly stage or spotlight are valid ImageNet labels, and we could have asked our annotators about them, but we didn't. So in that sense, the questions that we're asking our annotators when creating this data set is actually a very leading question. Is not, we're not just asking them to annotate what is in this image, we're just asking them, is this label part of this image? So now at this point you might ask, okay, but is this something that really affects the way this data set reflects the real world, or these are just some cherry-picked examples that I picked? And in order to do this systematically, we need to at least spend some time and get some understanding of what exists in these images. So if I show you this image, how do you know what's inside it? How can we even study the dataset if we don't have a good characterization of these images? So what we can do is we can try to actually collect annotations for every single class in ImageNet. So take the list of ImageNet classes and ask annotators, is this inside, tell us for every single one of these classes, whether this class is inside this image. And of course, this is too intense to do. Sure, if you ask these questions and people had infinite time to spend on this image, they could tell you that, yes, there is a neft, it's this little lizard, and there is a bottle cup, and none of the other classes are there. But of course, people don't have time to, we cannot just have annotators spend a ton of time on every single image to try to tell us what is there. But it turns out that you can do some simple pre-processing and some simple crowdsourced annotation tasks that unfortunately I don't have the time to get into. And you can limit these options to, let's say, the most probable labels for these images. Let's say by filtering labels through a machine learning model. And then it's actually feasible to ask annotators which of these potential labels are part of this image. And they will tell you that, okay, there is a neft and a bottle cap, and that's it. So overall, if we actually spend this time to collect fine-grained annotations, we can actually get an idea of what are the classes that are present in every image. So this gives us annotations that are much more rich than the ones we had originally for ImageNet, where all we had is the label that was part of the original dataset. So now that we have these fine-grained annotations, can we take a deeper dive and try and understand what is there in ImageNet and what things could be weird? And one thing that comes in mind is, okay, how many of these images actually have multiple objects? And when I talk about multiple objects, we don't just mean random clutter, but we mean objects that are part of ImageNet. There is a label about that object, but are not necessarily what the label contains. And this is a histogram. So on the x-axis, we have how many objects annotators selected as being part of this image. And on the y-axis, how many images are in that bucket. And it's important to mention that we asked annotators to only select a single label per object. So even if they were confused about the specific breed of the dog, they should only tell us that there are two objects if there is, let's say, a dog and a football. But they should not select two objects if they're just confused between multiple labels for the same object. And in summary, it turns out that more than 20% of the ImageNet test images contain more than one labels. Basically, these are things that if you ask the human, is this object in the image? They would say yes, and this is a valid ImageNet label, but these are not what the actual label is. And many of these examples actually make quite a bit of sense. For instance, you have this image where the label is microwave. But of course, if you ask humans if there's also a wash basin or refrigerator in the image, they will say yes. And it turns out that such co-occurrences make sense. There are, in fact, many consistent co-occurrences in this data set. For instance, if you look at the pairs of classes that most frequently co-occur, you get things that make a lot of sense. For instance, every image that contains an aeroplane contains an object that is a wing, or every image that contains a table lamp also contains a lampshade. And very often, if you have a desktop computer, you have a desk. So this also tells us gives us an important takeaway that when you're building an image recognition dataset based on the real world, the fact that you pick classes that are disjoint, in the sense that, oh, a desktop computer is a different object than a desk, this does not mean that your image distributions will not be overlapping. There will be many images where both of these labels will be valid. So, of course, the natural question to ask now is, do these images actually affect accuracy? And the answer is yes. Now, if we look here at this plot, what we want to look at is, on the x-axis, we're going to look at the test accuracy of a specific ImageNet model. And on the y-axis, we're going to look at the accuracy of this model on a specific subset of our dataset. So here, the blue line is the accuracy of a model on the images that we determine to be multi-label. These are images where most of our annotators told us contain more than one valid objects. Whereas the orange line contains images that annotators judged as containing only one object. And you can see a pretty clear difference. You see that models are doing much better on images that contain a single object and are actually quite more confused when images contain multiple objects. And if instead of measuring the accuracy of these models, you measure instead how often is their predicted label part of one of the labels that humans indicated as being present in the image, then you get this green line, and models are actually doing much better. So if you take a step back, what this tells us is that when you judge a model by its accuracy, very often this model will predict some label that is part of the image, but we say, oh, the model is wrong because it doesn't match the label that this image has in the dataset, even though the model is actually correct because it's predicting something that's present in the image. And a natural question here is, okay, but maybe this is happening because, okay, there's a clear main object, and the fact that an object is not in the image doesn't mean that you should be predicting that object. But well, there turns out to not be the case. There's actually a sizable set of images where the object that the models predict are not exactly what humans would consider to be the main label of this image. And the examples turn out to also be quite intuitive. For instance, in this image, the ImageNet label and what all the models predict is Pickelhaube, is this pointy hat that all the soldiers wear. Whereas the label that annotators said is the main image, is the main label of this image, is military uniform, which is again a valid ImageNet class. And in a very similar sentiment, you have an image of a suit, but both the ImageNet label and what the models predict is bow tie. And the same thing here for bellcote and church. Bellcote is this part of the church where the bell is at. So all of these are examples where human annotators see a very clear main object in these images, but the ImageNet label and what models predict is a very specific object inside these images. So in some sense, this ImageNet distribution and our models as an effect tend to overfit to these distinctive characteristics. So, and this makes sense from the perspective of accuracy. We're trying to get our models to be as accurate as possible. And of course, if there are things to exploit, then these models will exploit them. For instance, every time you see a bow tie, there's not necessarily a suit, but if every time that there is a bow tie in a suit image, then the label is bow tie, then your model should learn to predict bow tie whenever there's a bow tie. So to some extent, you might find this desirable. Our models are able to extract every single correlation they can about this dataset. But on the other hand, you might be a bit concerned. You might say that clearly these models are not learning what the real world looks like and are not learning to recognize things the way humans do and the way we intend them to. Okay, so what I want you to take away from this dive into ImageNet is that trying to design how our models work by just showing them data, while very powerful, is also very tricky. Even in this case where ImageNet was the result of this huge effort with tons of money spent on annotation and data collection, and you still, even if you try to collect this data set very carefully, you end up with all these weird artifacts that deviate from the way the real world works. And of course, the problem here is twofold. First of all, capturing the real world through images is hard. How can you even get a uniform sample of what real world images look like? And on the other hand, it's hard to be unbiased when you do that. For instance, we were not able to just collect images of bow ties in every possible scenario. So our models learned this weird thing that wherever there's a bow tie, they should ignore whatever other image class is there and just predict bow tie. So you may ask, okay, so if our models learned these weird things during training, and if they don't exactly align with how we want them to predict, what can we do to fix them? So basically, let's accept that no matter what we do, we can do our best to get good data for our models to learn from, but in the end, we will embed some biases and some weird behaviors that our models will pick up. So what can we do about it? And the standard answer is perhaps fine-tuning. Let's just collect extra data and retrain the model on this data to make sure that the model is doing the right thing. But the first problem with that is that this is expensive. Collecting data is not an easy task, and getting our annotators to annotate all the data is not the simplest option. And B, it's again not a very direct way of specifying model behavior. The reason we have all these weird things is exactly because we defined the way we want our model to behave by showing it some data. So now, if again, we collect another set of data and we ask our model to infer what is the right thing, it's not entirely clear that the model is going to do the right thing anyway. So is there a more direct way of specifying how our model should behave, how they should be predicting and what they should be doing? And it turns out that yes. And I want to talk about this recent method that we developed for editing the way models make their predictions. And for that, the primitive I'm going to start with is this primitive of single layer edits. So this was prior work from David Bao and collaborators. And in order to describe the setup, the best example is the following. Let's say that you want to edit a generative model, a GAN, so that wherever it produces a church spire, it should produce a tree instead. So before, your model is generating something like what you see on the left, and afterwards you want the model to generate what you see on the right. So how can you do something like that? Well, the key idea is that you can treat every layer as a linear associative memory. So what this means, this is a very simple concept. Basically, what you're saying is, okay, let's look at the model. This is our network with its multiple layers. And let's look at the part of the model that generates this spire. So if you look at these locations in the image, through the process of the model, you see how these pixels are represented in the latent locations through the model flow. And you could say that, well, maybe you could think of the representation of these pixels in these latent layers as containing some code that encodes spire. So every pixel corresponds to some vector, let's say 100-dimensional latent vector. And let's say this vector encodes what we view as spire. And basically, these vectors get transformed through the flow of the network to produce whatever pixels we see. So if you want to perform this edit, how would you do this? Well, you can take a look at the specific layer with weights W, then look at how spire is encoded before that layer, then look at how tree is encoded after this layer. So you manually edit the image, and then you say, okay, if my model was to generate this, what would the code have to be after that layer? And then you update your weights so that whenever your layer sees something that encodes spire before, it should encode tree after. And the interesting thing is that this update generalizes, actually. So when you do this update on a single image, it turns out that many other churches that you generate down the line will also have trees instead of spires. So we started from this primitive and we said, okay, so there is a way of changing how our model transforms individual concepts. And this is really cool. So is there a way of applying this principle to classification and trying to edit an actual predictive model? And for this, we need to look at things somewhat differently. So the example to keep in mind is, let's try to make sure that we're able to recognize vehicles whenever there's snow on the roads. Yeah, this is not too relevant here in California, but yeah, if you were in Boston where I did my PhD, well, you have to be able to recognize things on snow half the year. So let's say that you have your model, you put this image of a police car as input, and you want your model to be predicting police car. But now imagine this hypothetical scenario where you replace the road with snow, and then suddenly your model predicts husky. So how can we fix this behavior? Well, the key is that you have to think of models as predicting based on some conceptual high-level rules that make sense. So you could imagine that, well, our model is making predictions based on matrix multiplications, but in reality, it does operate based on some simple rules that we can make sense of. For instance, wherever there's road or wherever there's a wheel, these are indications that a police car is in the image, whereas if there is yellow, maybe this is indication that banana is in the image. And the way these rules are implemented, let's say at a specific layer W, well, this layer takes as input some representation of some concept and maps this to some other representation down the line. So whenever you put something that encodes road in the input, the output is a different representation of road. Or if you have yellow as an input to this layer as a code, then the output would be something that looks like banana. So from this very cartoonish representation of things, like obviously this is not how these models work, but if we imagine for a second that this is how they work, then making sure that the model correctly recognizes vehicles on a snow road is actually quite simple. We're saying that on top of all these rules, whenever this layer sees snow, I want to make sure that it's mapped to road after that layer. And then I'm going to forget about everything else because I'm assuming that the rest of the network is implementing some other prediction rules that will predict correctly police car as long as the bottom of the image encodes road. So in a bit more detail, what this looks like is we start from the original image where we put in police car and the output is, we look at a specific layer and we look at the bottom part of the image, which encodes road. And we look at how this part of the image is mapped into the intermediate layers. And we have something that resembles road before the layer, road after the layer, and leads to the prediction police car. But now what if we instead have snow at the bottom of this image? Well, then the same part of the image maps to some internal representations that encode snow before the layer, snow after the layer, and we get a prediction that says something like husky. So now if we want to update the model to correct it, what we do is we say, okay, I want to change this specific layer with weights W so that the before part in this specific region of the image where I had snow now maps to the other representation that actually has road for the corresponding pixels. And when I do this update, then after that layer, instead of snow before, I will have road, and then I'm going to fix the prediction of the model to actually be correctly police car. So this is the overall method at a high level. And even if you don't really get all the details, that's fine. But the key idea is that basically it's a very conceptual method. You're able to say that I want these pixels that encode something to instead represent what they were representing in this other version of this image. So we're saying that the snow part of this image, I don't want my model to see snow. I want to see what it was seeing when there was no snow there. So yeah, at this level, it's like something very intuitive, and I hope it makes sense. But perhaps it becomes more concrete when we see some examples. And it's important to stress out that this is actually something that you can do using only a single example that you create in a syntactic manner. So here we didn't have to do any data collection. All we did is exactly what I'm showing you. We just put some snow texture and perform this method. So the question is, does this work? And what better setting than to look at it than what we discussed so far, vehicles and snow. So what we did is we went through Flickr and took a bunch of ImageNet classes and searched Flickr for images of these classes on snow. So we searched for fire truck on snow, traffic light on snow, school bus on snow, and so on. And we got all these images. And how well, yeah, and the model is having some performance on them. How much doesn't really matter because these images could be out of distribution. But the question is, can we improve the performance of our model on these inputs by performing the rewrite that we just talked about? So what we do is we take a single example of this image on a police car, of a police van. We annotate the part of the road. Now we manually transform it based on some snow texture that we found on Google. We annotate that part again. And then we say, I want to map snow to road. So whatever representations were in this part of this image, I want them to be the same as the representations in the original part of the image where we actually depicted road. And it's important to note here that police van is not in the class that we actually look at our performance on. So once we do this update from snow to road, how does the performance of our model change? And here there are three methods to look at. The gray is the original performance of the model. And then the dark blue is our performance after we do the edit. And you see that actually the performance of the model improves quite a bit. For instance, for images of racing cars, it increases by quite a bit. And as a baseline, we look at the performance of fine-tuning when you fine-tune the model on this specific image. So we don't collect a lot of additional data. We just say, okay, let's try to fine-tune the model on this very specific image and make sure that on the version with the snow, it actually predicts police van correctly. And this is the pink line. And you can see that this doesn't improve performance at all. And this makes sense, right? If you think of what are we trying to distill into our model, when we perform this fine-tuning, all we're saying is, I want the model to predict police van on this image. And there are many ways to do it. One of them is to learn maybe to make police van more likely as a label, or associate wheels more with police van, or maybe learn that police vans appear on snow, but this is only one way of doing it. Then there's no way to make sure that our model is learning the correct thing from there. And yeah, and if we want to look at another example, there's this very interesting phenomenon of these typographic attacks. So basically, there's this phenomenon that if you look at clip models, these are models that have been trained to jointly encode language, text, and images. There's this phenomenon where if you take an image of an apple and the model correctly says that this is a Granny Smith apple with 85% confidence, and you write the text iPod on it, then suddenly the model gets confused and predicts iPod. And these attacks were observed by Go et al. So what we did is we did our own reproduction where we found these attacks actually be quite easy to do. You just take a number of household objects, you add a little note on them that says iPod, and then suddenly the model predicts iPod on all of them. So the question is, can we make the model ignore the test iPod? So can we make sure that our model is making its prediction without taking into account the fact that there is a text iPod in there? And if you take a moment and think, then, well, the editing pipeline that we talked about so far is actually a great way of doing this. So what we can do is we can take, again, a synthetic example. This is an image of a can opener, and we synthetically write iPod on it. And now we annotate this part of the image. We replace it with a white square. And then what we want to do for our model is we want to say that I want to map the text iPod to nothing. So here we're doing the edit the other way around, and we're saying that I want whatever representation these iPod pixels have, after the layer that I'm editing, I want them to transform to nothing, whatever white would be. And again, we're doing this edit on this single image. And well, if you do this, then the prediction of the model gets correct on all the images that was making the mistake before. Basically, for every single one of these images that the model was predicting incorrectly, and it was fooled by the text iPod, now it's not getting fooled anymore, and it's predicting the underlying object correctly. And again, it's interesting to contrast this with trying to fine-tune on this example. Basically, take this example and train your model to predict the can opener, the original label. And if you do this, what will happen is the predictions of the model will change, and you will become correct in some of these examples. But in many other examples, you will see that the model is predicting can opener, because basically what is happening is not only it's associating the text iPod with can opener, but sometimes it's even increasing the weight of can opener by quite a bit to make sure that it makes the right prediction. So it even predicts unrelated objects as can openers. So, and we tried quite a bit. We said, okay, there must be a way to train the model on these images and make sure that this doesn't happen without editing. And we couldn't find a way of making sure that the accuracy of the model doesn't drop too much, or making sure that it doesn't predict can opener everywhere. Whereas in contrast, when you do this editing pipeline, it works really reliably. You do it, the first thing you try, you just do it and it just works. So these two examples were nice in the sense that they do both capture real world test cases that you could care about. One of them is you're trying to adapt your model to a new environment where you have suddenly snow on the road and you want your decisions to be made differently. And we collected real world images. And the other example is, again, you have an example of real world objects that get misclassified when you change something. And we were able to successfully make our model ignore this spurious feature. But of course, these are only two scenarios. And we really wanted to test our method on more things. But it was tricky. It was not super easy to come up with examples and also find the corresponding real world images to do that. So what we did is we came up with a benchmark for editing methods. And the key idea is that what we want our model to do, what we want to do is we want to edit a specific prediction rule in our model. So what this means is we want the model to change how it treats a specific object through its pipeline. So in order to do that, we start from a diverse collection of images into a standard data set, let's say ImageNet. And then we annotate specific objects through instance segmentation. So we just use pre-trained instance segmentation models to identify various concepts that are parts of these images. And then what we do is we transform these objects by applying style transfer. So what this does is it changes the appearance of these objects in a way that sort of preserves realism. Like if you see the trees go from having a winter vibe to having a fall vibe, and without completely overriding the leaves and all the fine details that are there. And one thing is that, okay, this is something that you can do using only pre-trained datasets. We didn't have to train any models to perform this transformation. And the important thing to keep in mind is that we are transforming objects in a way that is consistent across classes. So basically, if you have trees in images of cars and trees in images of dogs, then both of these get transformed in the same way. So when we perform this transformation, because we're doing something weird with our data set, the performance of our model drops. Right? So if the model is using trees to detect slope, then the performance of our model will decrease. And the question is, can we edit the model to improve the performance of the model on these unnatural transformations? So for instance, the idea is if we're able to teach the model that the trees that appear in fall color are actually the same as trees appearing in another style, like winter trees, then we would be able to make our model perform better. And we looked at this specifically in the context of two settings. So one of them is ImageNet with a VGG16 classifier, and the other one is, let's say, Places with a ResNet18 classifier. And what we care about is we want to ask how many of the errors that these transformations cause are corrected. So obviously different transformations will cause different amounts of error, so it's hard to compare between classes, but we can at least ask, out of the mistakes that are caused by these transformations, how many of them can we correct? And specifically, we're going to look at a couple of different methods. One of them is editing. The minus mask is just a small ablation that we did. And then the other baseline is local and global fine-tuning. And again, we try to fine-tune the model using the exact same set of images. Like here, we do this editing process and the fine-tuning process with 3 images. So we perform either global fine-tuning, where we train the entire network end-to-end based on these images. So this allows the model to adapt the most. And we also try local fine-tuning, where we only train the layer that we perform the edit on. So this sort of places it in a bit more equal footing as editing. Yeah, so we're testing both of these. So how well do we do? Well, the first thing to look at is if we perform these edits on images of a specific class, how well do these edits generalize to other images of this class, either using the same style or using similar styles. And here you see that both editing and fine-tuning do improve. They do correct many of the errors that are caused. And in some cases, turns out that fine-tuning actually fixes more errors than editing. But what is more interesting is what if we look instead in the other cases, in other classes? Basically, we look at classes that contain the same object, but were not part of the editing that we did or the fine-tuning that we did. So this is saying, I'm going to make sure that I'm going to fine-tune my model on images of dogs where trees have been transformed and fine-tuned on. And then I'm going to test my model on images of cars where I apply the same transformation to the trees. And here we see that actually, while editing still helps quite a bit, fine-tuning actually hurts many times. It doesn't really have consistent improvements and very often ends up hurting more than it's helping. So even though it's making the model predict correctly on these classes more often, it doesn't really help the model learn and generalize from this transformation. And as an aside, I want to talk a little bit about, so if you take a step back, what did we do in this process that creates our benchmark? What we did is we said, okay, take a specific concept and transform the way that it looks across all classes. So we're in some sense creating a counterfactual, and we're asking, how would the model predict if this specific concept was transformed? Well, on one hand, we could ask, okay, can we fix the robustness of this model to these transformations? But if we flip this on its head, we can ask, why does the performance of the model drop? And how much the performance drops does depend on how much the model relies on these concepts. So if I transform trees and the performance of a model really drops, then it means that my model must be relying on trees to make these predictions. So in other words, accuracy drop actually reveals concept sensitivity. So once we do all these transformations and we ask for different concepts and different styles, how much does the performance drop, we can do a pretty nice analysis of model behavior. So for instance, we can focus on a specific concept, let's say grass, and ask which classes is our model sensitive to grass on? And it turns out that things like croquet ball are quite sensitive to grass, whereas things that like collie, which is a dog breed, are not particularly sensitive to grass. And from these examples, you can actually see that the amount of grass that there is in the image, even though collies appear very often on grass and they're actually, most of the image is grass, changing the grass to something else doesn't really hurt their performance, which indicates that the model is probably relying on different features to recognize them. Whereas for things like croquet ball or kid folks, the model is actually relying pretty strongly on the presence of grass to classify these objects. And then you can do an aggregation based on sensitive to different styles. So if I replace objects with graffiti patterns or floral patterns, it turns out that performance drops quite a bit. Whereas if I replace things by metallic patterns or black and white patterns, then the performance doesn't really drop by that much. And finally, you can look at, say, if you look at a specific class and you ask which objects actually affect this specific class. So this is looking at something similar to the first plot, but in the other way around. So here we have the plots for groom. This is, the person who, like the man who gets married. And it turns out that, okay, this is sensitive to things like dress suit. And this makes sense. Having a groom being sensitive to the presence of a suit is reasonable. But at the same time, this class is also sensitive to things like flower arrangements, which is, okay, maybe something that does indicate the presence of a groom, but is clearly a spurious feature. So for instance, by doing this analysis, you can see that the model is relying on the presence of flowers to detect the class groom. Okay, so to conclude, what are the key takeaways? So the first important takeaway is that, okay, data is actually a very unreliable way of saying what you want your model to do. While we all agree that it's a very powerful paradigm, you can say, I'm going to collect all this data without thinking too much about it, and my model is going to learn a lot of useful things based on that data. It is not easy to fully control the behavior of this model by just making sure you collect the right data. So it turns out that there are actually ways of directly rewriting the predictions of our models. There are ways of going into the model internals and saying, okay, how is the model predicting on this class? I want to change this a little bit. I want to make sure that my model is doing something different than what it was doing before. And at a more broader point, we tend to think of these models at a very black box way, as in what classes do we put as an input and what is the accuracy of our model of these classes. But one of the things that I took out of this project is that if you start thinking instead in terms of high-level concept that your model is operating based on, then this can actually be much more powerful and can give you ways of both understanding what your model is doing and changing the way that it behaves. And going forward, I think that there are actually many exciting directions here. So on one hand, can we design better ways of collecting data? Like in the end, it's clear that most of our machine learning will happen from collecting data, and trying to find ways to collect data that reflects the real world in still a way that is scalable and easy to do is very important. Then moving beyond that, we saw this primitive of concept rewrites, basically saying that the way my model treats this concept should be somewhat different. And we saw that this basically allowed us to improve the performance of our model on a variety of instances. And in prior work, they found that this allows you to edit the way your model, a generative model, makes its predictions. So what are other things that we can do based on this simple primitive? And then zooming a bit more into this method, can we write many rules at once? For instance, here we saw examples of editing individual rules, like, oh, what if we edit road to snow? But the problem is that these often cause a slight drop in accuracy. So if you start compiling many of these edits, like if you wanted to start with a single model and actually make many edits of many different things over time, then this could quickly hurt the performance of your model. So what are better ways of doing this? And finally, perhaps at a slightly more interpretability focused question is, if you have a specific distribution shape that you care about, there is some environment that your model is not doing well on, maybe we can use our expertise and say, oh, I think these are the things that I should be changing in the way my model behaves. But what if you don't really know them? What are good ways of sort of discovering what these rules are and what is failing so that you can actually rewrite the relevant prediction rules into your model? So to conclude, all this work that I presented was based on roughly 2 big projects. One was based on the paper from image to image classification that we did back at MIT with my collaborators, Shubhani, Andrew, Logan, and Alexander. And the second one is in collaboration with Antonio Torralba's lab, with David Bao and Mahi, based on editing classifiers based on their prediction rules. And we have blog posts and links to papers and code and everything in the MIT lab blog. So you can go there if you want to learn more things. And I'm happy to take any questions that you have.
Thank you very much for a great talk. Hi, audience. If you have any questions, yeah, feel free to ask here. Basically, from my end, I have a question. I type it in the chat box while you are talking. So when we edit the classifier, where the feature and the weights get entwined over the depth of the layers, this may increase the difficulty of the editing the classifier.
Yeah, so that's a great question. So yeah, so when we started this project, we were thinking that, okay, maybe different prediction rules happen at different parts of the network. So maybe the car wheel to car happens at layer 6. So maybe for every specific edit, there's a specific layer that you should be doing it. But this turned out to not be the case. Like we tried to do quite a bit of hyperparameter optimization, like trying to run this thing for many layers. And almost always it performs better when you do it in the later layers. So it seems that the model has captured more things about the input and understands more about high-level concepts like wheels or trees and so on, that doing it later makes it much easier to get good performance. Yeah.
So basically, the previous layer is more like a feature extractors. Then the layer is later is like the classifiers to.
Exactly. Yeah. Like I think this is
I see.
Yeah, that's consistent with our observation. Yeah. But yeah, just to mention that it turns out that when the previous work did this for the case of guns, for generative models, they did find a difference between layers. So they did find that for some specific edits, they're better to do at layer 4 as opposed to layer 6 or something. So maybe this is telling us more. Yeah, so it's a bit tricky because is this telling us something about the way editing works, or is it something that tells something about how our models work? Maybe generative models and classifiers work differently in the way they organize concepts. So yeah, that would be really good to understand a bit deeper.
I see. Thank you. Yeah. Also, I have another question. For example, we know that the norm of the mathematical norm basically cannot accurately capture the concept what humans perceive. For example, the LP norm cannot accurately capture the the concept. For example, the snow, the object. So basically, we have to manually to circle out the specific project we want to edit. So is there any way to automatically do that, without human intervention or the automatic pipelines for doing this? Oh, yeah.
I see. Yeah, that's a good question. So in this specific case, because we're doing this edit based on a single example, that's sort of fine in the sense that like, as an interface, you only have to do it once for a single image to turn snow into road.
Sure.
But more generally, I guess the question is what is the interface that you're having? And if you want to perhaps work maybe with text, like saying that, oh, I want snow to map the road, then it could be possible to actually take advantage of these instance segmentations and say, okay,
yes,
can I use an instance segmentation, model to detect snow in images, and then detect road and make sure that these representations match?
I see.
And something like that could be interesting because basically it will also provide you with access to every single class that instance segmentation models work with. Yeah. I guess there are a few different scenarios that like you could imagine. Like in my view, for instance, this is more of a tool for working with cases that are not that well represented in the data. For instance, the iPod example, like I don't really know what you could do automatically, right? Because there's no clear segmentation that says there's a text iPod there. So, or maybe you have some new unusual type of a wheel or some unusual clothes, and you want to say, oh, this unusual thing is not something weird. It actually corresponds to this concept that we already know about. So
yes,
yeah, I guess you could view it both ways.
I see. Okay, thank you very much. It totally clear my questions.
Nice.
Hi everyone. If you have any questions, you can ask here now. If not, yeah, maybe this is the end of our seminar. Maybe in the future you can also email Dimitris to ask his questions.
I'm happy to answer any questions over email.
Yeah. I hope when the situation is lifted in Japan, we can sincerely welcome you physically in Tokyo in the near future.
That would be fun.
Yeah, yeah, that would be fun. Yeah, the Nihonbashi office. It's quite a good place near the center,
nice.
In the center of the Tokyo. Okay.
Nice. Never been there.
Yeah. Okay.
Right.
Thank you. Bye bye. Thanks.
Bye.
Again for your quick talk. Bye bye.
Thank you. Bye.